Welcome back to Lesson 2 of a course in set theory, logic, and inference. It's important to talk a little bit about the history of this field. It has its origins in philosophy. Probably the first logician was Aristotle, but he was working in a very informal logic, and it's only in more recent times, say in the last 150 years, that people have formalized the notions of logic into a precise mathematics. And the work in this field has spanned philosophy, mathematics, linguistics, and now also computer science. And we'll talk as we go forward, mentioning a few of the important names in this field and their contributions. So in computer science, you could really say that logic is the foundation. After all, circuits are logical operators, and circuits in a microprocessor in a computer are performing logical operators to do their job. And understanding logic is also very important in understanding the basics of computer programming. And we'll see this in an exercise that we'll get to shortly. There are many applications of formal logic in computer science. Probably the most prominent is in software verification, so very high risk, where high degrees of trust are needed for the execution of a computer program. These methods in logic provide a way to verify that the software will work as intended, not just through testing, but through rigorous mathematical proof. And there's also a long history of using logical methods in artificial intelligence. They're less prominent or popular now, but they haven't gone away, and we'll talk about some of those as well as the course goes on. So one of my favorite quotes, I think one of the favorite quotes probably of many people working in logic, is credited to Leibniz, who after some arguments about possibly things in politics or philosophy, came up with this very nice quote about, wouldn't it be wonderful if we could just calculate in order to resolve disagreements? So his Latin phrase, calculemus, let us calculate. And the elaborated version of his quote is, if controversies were to arise, there'd be no more need of disagreement between two philosophers than between two calculators. We would just pick up our pencils and calculate. And what a wonderful dream. And I think there is some merit to this. If people are forced to write down their beliefs formally, then at least some basic misunderstandings can be avoided. Of course, in reality, it doesn't mean that everybody has the same premises, and that seems to be a real sticking point in a lot of disagreements. But at least we can eliminate problems about communication if we were to communicate our arguments in a formal way and adhere to the principles of mathematics in that formal logical argument, so that we weren't creating chains of spurious or fallacious reasoning. So deduction methods are one way, possibly, of automating rational thought. And in order to do that, we first need unambiguous specifications. We need a syntax for our language that specifies what are the symbols and how do they fit together, what are the mechanical rules that govern the language that we are going to use. Because we won't be able to deal with sort of approximations or ambiguity in the way human language does, because we won't have necessarily a human in the loop. We want a mathematics that just follows rules that we can use to calculate the answers, and we want our computers also to be able to follow those strict rules. We also need a semantics. We need to know that if we do manipulations with these symbols, what does the result actually mean? How does it relate to some real or hypothetical world? And we'll talk about this as well as the course goes on. We want to be able to derive objectively correct knowledge. And so therefore we need to know, what does correctness actually mean, and how can we ensure it automatically, and how can we derive new facts automatically? How do we ensure that, given a set of premises or assumptions about our world, how do we employ rules that transform those statements into other statements and know that we're not introducing errors as we go along? And that's really what makes this this whole field a mathematics, in that we do ensure that things are truth preserving. If we start with things that we assume to be true and we do our calculations, we will wind up at the end with things that are guaranteed also to be true. And that's the fundamental about mathematical proof. It's not a proof if there's any doubt about each of the steps in transforming from assumptions to conclusions. So let's look at a particular application example that involves determining whether specifications are equivalent. And we can imagine a sort of typical software development process where there's a customer who has some specification, usually fairly informal, of what he or she wants. That is turned into a system specification by a systems analyst or computer programmer, and then into a software design that specifies more specifically how we're going to use some sort of computer or language or system in order to achieve a result. And with that design in place, we can go off and implement. And of course, this would be an iterative process most of the time nowadays, maybe using an agile methodology. So there'd be many cycles of this sort of process. The problem is, how do you know whether each of these different levels or steps are resulting in some things that are equivalent? If you just have an informal specification in natural language, or maybe it's even more informal, it's just some conversations that maybe are not tracked particularly well in writing, then it's going to be difficult to know whether you've implemented something that is actually what the customer wanted. And this is why we have highly iterative methodologies like something like Agile, because that process is so error prone. Sometimes even the customers may not know exactly what they want. And so we're just trying things, iterating to try to get to a good result that is something that the engineers can implement and that the customer is also happy with. But manual checking is complicated and it's error prone. It's not always clear whether the code implements the specifications. And any sort of initial specification might not actually be feasible. It might be unknown as to whether it's possible to meet certain objectives. So the more formal we can get in this process, if there's an easy way to do so, the better off we're going to be. And at least for this case of equivalence of specifications, if we formalize those specifications, there is a precise method we can use, and that's the method of deductive logic. So let's get more specific. This is just hand-waving so far. How do we put this into practice? So let's take a particular application that my colleague Stefan Schultz actually was the lead on implementing, where he worked for an air traffic control company. So here's just a very brief sketch of the air traffic control problem. You have lots of planes flying around in the sky. Some are in controlled airspace, right? They're either at an altitude where they can interact, potentially poorly interact with other aircraft, and particularly at lower altitudes around an airport where they're landing or taking off. Those are particularly critical areas, quite obviously. Right? And the players in this scenario are radar systems that tracks these aircraft, an air traffic control center, possibly a regional air traffic control system that's away from the airport, that's managing the high altitude transit of these aircraft and their potential interactions. And then there's also the airports, obviously, where there's a control tower managing the takeoff and the approach and maybe doing some sort of handoff to the regional air traffic control system. Here's a depiction of what the air traffic controller sees, and obviously this is a complicated, high-stress, high-risk job where you really have to get things right or you have accidents and loss of life, obviously, and it's a complicated process where there's a lot going on at any given airport, particularly a very busy airport. We're going to look at the Dubai airport as just our notional example. You've got tons and tons of planes coming in, taking off all the time. And how does one air traffic controller keep that stuff straight, right? You've got a diagram that looks like this. To the untrained eye is pretty unintelligible and pretty complicated. So one of our goals in designing a good air traffic control software system is to limit the cognitive overload of the air traffic controller. Only show them the things that really matter and hide the rest, because anything else is going to be a distraction. So we're going to need information like the boundary of a particular sector, where air traffic control might hand off to a regional system, or where there's something like a restricted area or certain kinds of controlled airspace. Maybe there's a practice area for new pilots where you don't want the commercial air traffic going through, because that could be disastrous, especially with untrained pilots. We've got a host of different airplanes. Those airplanes are on particular flight paths. Those flight paths may have waypoints. And for each airplane, the air traffic controller needs to know, what is that plane? It's going to have a particular identifier along with its altitude and speed, so that if some direction is needed, the air traffic controller can contact the pilot on that flight and give them that needed direction. So air traffic controllers need to see only the relevant traffic. And let's take a very simplified example of that. Let's say we have airplanes in the controlled airspace are the only ones that pilots, that the air traffic control needs to worry about. If they're in uncontrolled airspace, it's just not their job. Right? And this means all planes near the airport on an approach or taking off, and airplanes that are at a given altitude. So if they're not near the airport, if they're above a certain ceiling, above a certain altitude, then again the air traffic controller just doesn't care. It might be a drone flown by a hobbyist or birds or something of that sort. They just don't need to pay attention to it. Right? And another exception is if they're military aircraft within some training area, then that's not the responsibility of the civilian air traffic controller. That's the responsibility of presumably some military organization. Another challenge for this in practice that my colleague had to deal with is that there are different demands from the pilots. Things change, and we want our software to be as flexible as possible while at the same time being quite rigorous, because the cost of failure is very high. So we can't hard code in solutions. We've got to have some way to make a specification that can be changed and then also verified. And the way he went about this was through logical expressions and using deductive logic to prove the equivalence of these specifications to make sure that we didn't have some terrible disaster resulting from faulty coding. Developed an elementary filter which included the elevation of the aircraft, its ID, or also a determination of what that aircraft actually was, and then a geographic filter that could say, is that aircraft in a region we need to care about, or in a military region, or a training region where the air traffic controller doesn't need to worry. And the aircraft then would only be displayed if the filter expression evaluates to true. And here's a representation of, again, a simplified version of the filters used in practice. So notion of a relation in region, which is a polygon that is a particular region that we care about or that we don't care about. The altitude of an aircraft is between some lower bound or not, and whether an aircraft is on a certain kind of list, specifically a list of military aircraft or civilian aircraft is the dividing line here that we have in this particular application. And then we also have some specific filters. This example looks at the United Arab Emirates and the airspace there, looking at Abu Dhabi and Dubai. So AD is Abu Dhabi, DUB is Dubai. And so we need to determine whether the aircraft is in those regions, if it's in a military region, if it's in lower airspace, so an airspace that outside of the immediate region of the airport the air traffic controller doesn't care about, or the upper airspace where he or she does have concern with that aircraft. And then also the determination whether the aircraft is military or not. If it's military, you don't have to worry about it. That's somebody else's job. Right, so the first expression that we come up with is draw the plane if and only if it's in lower airspace and approaching in the approach region, or also the takeoff region, but we'll call it the approach region of Abu Dhabi or Dubai airports. Or whether it's in the upper airspace. So it's completed its takeoff and it's now flying at a higher altitude where it potentially could still interact with other aircraft to bad effect, and we need to pay attention to their flight paths. And also we want to display something only if it's not in either a military region or a military aircraft. Okay. And we're going to be concerned also about the interpretation of this formula. So I've highlighted this in red because it's a word we're going to come back to. We're going to have a mathematical approach for determining how do we interpret these symbols, how do they relate to things in the world. For now, we'll just be looking at this informally, but later on we'll be very formal about this. So some implementation details. Calculating altitude is cheap. We just say if it's a number greater than or less than another number. If we're filtering with regards to ID to determine whether it's a military or civilian aircraft, it's just table lookup. A geographic filter, however, as to whether something is in a given region, that's a spherical geometry calculation, and it's expensive. Or let's say it's so expensive that in this very high performance system, we don't want to perform that operation unless we really have to. And we also know that we're going to be using a modern programming language for the implementation of this, Python or Java or some other language, probably C++ actually for a high performance implementation. And that language has short circuit evaluation of Boolean operators, which means if we are evaluating a whole expression and we look at the first part of the expression, and that's first part evaluates to true or false, and it means that we don't have to worry about the rest of the expression. We don't just keep blindly going through it. So if we have something must be true and something else must be true, we evaluate the first thing and it evaluates to false. We don't need to worry about evaluating the second thing because we've already said we've got one false in our conjunction. So we've got false and something else. Well, false and something else is always false. So there's no point in evaluating that second expression. And that means, as a result, with that short-circuiting approach to evaluating logical operators, we get faster performance in our software. So we want to take advantage of that. So here's an optimized version that takes the complex calculations, the computationally expensive calculations of determining whether something is in a particular polygonal region, and it moves it to the end of the formula so that we can evaluate this first disjunction is something in the upper airspace or in one of the airport approaches. And if that whole thing evaluates to false, the whole thing is false. We don't need to evaluate the second part of the formula. So a very important thing to be able to do. However, how do we know conclusively that our optimized version of this formula is the same as the original formula? Right? So we're evaluating this original version that is up top with the revised version. We need to prove that those are equivalent. So how do we do this? So here is, I'm just throwing you off into the deep end of the pool, and we're going to look at a particular implementation of mathematical logic. So it's the TPTP syntax, a syntax that's the development of which has been led by Professor Jeff Sutcliffe at University of Miami, and it's a standard that's been adopted by almost all of the high-performance expressive theorem provers that are in existence. And this is what it looks like. If you study it, you'll hopefully be able to see the connection, how it parallels the formulas on the previous page. But for now, let's say, don't worry about it too much. I just want to present that there is a computational implementation of mathematical logic, and we can use this to solve our problem. And what we've done in this code here is take our two versions of this test and put an equivalence between them. That's the little arrow that faces both ways. So less than, equal, greater than, and kind of in the middle of your screen. That means that the two formulas must be equivalent. They must evaluate to the same logical value, true or false, regardless of the parameters that they are given. Right? So are the original and optimized versions equivalent? Well, the way to determine that is we set them into an equivalence relation, and we ask a high-performance theorem prover to prove that in fact they are or that they aren't. Okay. And if we run this in a modern theorem prover, we'll get a whole series of messages, but basically something that looks like this at the start and the end of those messages that's saying no proof. We actually haven't been able to find a proof that they are equivalent. Okay. So we want to be able now, knowing that there's a problem, go about fixing it. So the only problems here, only things that we can analyze are this lower and upper airspace. They're the only possibilities, right? There isn't a third thing. There can't be a middle airspace. But we haven't said that, and that turns out to be the problem. Right? So we can make that revision in our code, and then we'll be able to get a proper answer. Right? And if we make that revision, we do get the right answer, and it's found in a lot of steps, but a very short period of time, because modern theorem provers are super fast. Okay. So do we solve the problem, or do we represent the problem in a general way? This is another issue. Certainly a lot of people have the perspective that we just need to get to an answer as quickly as possible. And so if you're doing kind of one-off system, that's a good guide, right? Don't overcomplicate things. Don't try to think too much about the future. Just get your job done for today. And so that same philosophy gives us direction to, if we're just doing conventional programming, maybe we just want to write some quick script to solve a problem, or do something on the command line, do a process with sed or awk or something, or maybe use what programmers used to use Perl for quick text processing things. However, if we want to have an eye to the future, if we want our software to be long-term and evolvable, we may need to do something a little bit different. Okay, so we could say that to solve our problem, that we just have the lower airspace or the upper airspace, that however does allow for both situations to be true, and that's not true in the real world. It solves our problem of saying it's one or the other, or both. It will get us a proof, but that rule is potentially dangerous in the long term. What we really want to say, I think, is in the long term that there isn't a middle ground. It has to be one or the other, and not both. Right? So is our goal to just have the right answer as expediently as possible, or is it to create some code that stands the test of time? And it just depends on your situation, but keep this in mind, because this is something we'll also come back to. So I'd like to provide an exercise, which is build up a little bit of muscle memory. Try this example. I've given you all the code. You can just highlight it or type it in. I'll provide a link to a file so you don't have to type it in unless you really want to. And try this in Jeff Sutcliffe's System on TP system. It's web-based, online, and I suggest using the eProver. It'll probably give you the most friendly proofs. It's also extraordinarily high performance, and for students new to theorem proving, I'd say it's pretty clearly the right choice. So you would select E, you would paste the problem as we've developed it into the browser, and then click on Run Selected Systems. And for the moment, right, I haven't told you how to interpret this language, and I haven't told you how to interpret the proofs other than just looking for the result. Proofs can be challenging to understand without some training. So for now, just be concerned with looking for this proof found or no proof found message in the result, and that's all you need to know. So give this a try. Right, so to conclude this particular lesson, we came up with a problem about filter specifications for determining when an air traffic controller needs to worry about airplanes. And we did this specification in symbolic logic so that we can ensure that we've proven that our logical test is going to do what we want it to. And in fact, in the first version, it didn't do what we wanted it to, and the theorem prover was able to tell us that. And then we created a second version, which the theorem prover was able to prove conclusively was equivalent to our original statement. So this is the power of formal specification. It doesn't always need to be a really big thing. It's really handy even for small tests of this sort, especially, again, if you have really high-risk kind of situations that your software is governing, issues of life and death. You need your software to perform absolutely correctly, and deduction gives you the tool, one of several tools possibly, to actually do that, to make sure you've done the right thing. Okay. One other thing that I'll just allude to in naming, you might take a look at the following YouTube video. Be careful about what you call things. I've called it filter in this case. Is it filter out or filter in? That has an impact on the readability of your software, and so pay attention to names, and also pay attention to the fact that the thing that you use for a name, the symbol that you use, that seems very intelligible to you might not seem completely intelligible to the next guy. It might be misinterpreted. Keep that in mind. I think that'll help make you a better programmer. So thanks for watching, and see you in the next lesson.